Hello everyone. So in this example, we're asked to write a chemical equation for the oxidation of ethane by oxygen to form CO2 and water. Alright, and of course the fancy word, the oxidation of a hydrocarbon, actually just means to burn it in that hydrocarbon. And then to form CO2 and water means it's a complete combustion. It's a combustion reaction. So I went ahead and I wrote the reaction, I balanced it, so there you have it. It's a relatively simple equation to balance because we're given all the constituents and then go ahead and balance it. So then we're asked to, for this reaction, we need to predict several signs and do some discussion. It's a very qualitative conversation, right? There's no calculations, it's just predicting and doing things like that. So let's go ahead and do that. So the first question asks, we need to predict whether the signs of the entropy change of the system, surroundings, and the universe will be greater than 0, equal to 0, or less than 0. And we need to explain our prediction. All right, so let's start with the entropy change of the system. Will that be greater, less than, or equal to 0? And so for the system, entropy change for the system. And the best way to do that is to see from how many moles of gas are we going, how many moles of gas are reacting, and how many gas are being formed. So if we look at that, we see that there are 2 plus 7, so 9 mole of gas that is being reacted. 9 mole of gas reacts to form 4 plus 6 to form 10 mole of gas. All right, 10 mole of gas. So that means we have a net increase in the amount of gas. In other words, our system is being dispersed more, right, as the reaction proceeds from left to right, so as written. And hence, if there's a net dispersion, or there's an ability for the system to expand, the system to increase the energy is more dispersed, the matter is more dispersed as the process moves from left to right. That means the entropy change of the system must be positive, right? So it increases. So that is our first thing that we look at. Now the next question is, what about the entropy change of the surroundings? Right, so the entropy change of the surroundings. So the entropy change of the surroundings, is that positive or negative? And I mean, now we first need to think about how does one calculate the entropy change of the surroundings? Well, the entropy change of the surroundings will be given by the reversible heat exchanged at a specific temperature. And the amount of heat exchanged with the surroundings in this case will be just negative whatever the heat is that the system exchanges with it. So right, if the system gives off a certain amount of heat, the surroundings must absorb it. If the system absorbs a certain amount of heat, the surroundings must give that heat. So whatever the heat relationship with the system is opposite to that of the surroundings, right? So it's negative the system's heat. And the heat of the system is that at constant pressure. So in other words, that will be negative the enthalpy of our reaction, right? So because we're looking at the reaction, so that heat of the system is the enthalpy of reaction. All right, and our question therefore must be, what is the enthalpy of reaction? And that lies in some, let's call it almost colloquial knowledge that you must have or should have. What happens during a combustion reaction, or the so-called oxidation of a hydrocarbon? Combustion reactions are exothermic, right? So you must make a big note here for yourself that a combustion reaction is an exothermic reaction. So that means that heat will be released, right? So the enthalpy of a reaction, a combustion reaction, is always negative. Heat, it's a burning, right? It's a fire, you can think of it. So heat will always be released during a combustion reaction. So if that is negative, right, so meaning that this here is a negative quantity, it makes it minus minus, and therefore it makes the overall entropy change of the surroundings will be a positive quantity. All right, because the part of the value that you put in there is going to be negative, and we have to take the negative of that negative quantity, which make it a positive quantity. All right, so that just leaves then the entropy change of the universe. And of course, the entropy change of the universe is the sum of the entropy change of the system and the entropy change of the surroundings. All right, and because both of these quantities are positive, the sum of them will also be positive. So that's why the entropy change of our universe is also positive. All right, and that is why this will then therefore be a spontaneous process in this case. So this will definitely be a spontaneous process because the entropy change of the universe is larger than zero. All right, so look at that. You didn't do any calculations. You only used your basic knowledge to do a whole lot of predictions, and you learned a whole lot of stuff about this system. All right, so let's look at B. B says predict the signs of the enthalpy of reaction and the Gibbs energy. All right, so the first one is easy because we've actually already done that now. So the enthalpy of reaction, we said, is less than zero. And why? Because it's a combustion reaction, right? Combustion reactions have a negative enthalpy because it's an exothermic reaction, and it's because combustion reactions are always exothermic. All right. So now, so that's the enthalpy. The question is how do we get the Gibbs energy? Well, let's look at how does one calculate the Gibbs energy? And things that we already have is, of course, the enthalpy. All right, the enthalpy minus T, the entropy of reaction. And so the parameter that we need is the entropy of reaction. But hopefully, you recall that the entropy of reaction is just the entropy of the system, right? Because when you're looking at a reaction, your system is your reaction. So we've already made that prediction earlier. The entropy of the system, we said, is a positive quantity. So this is a situation where our enthalpy is negative minus T, and our entropy of reaction is positive, right? So we have a negative minus T multiplied with a positive quantity. So it's minus minus. In other words, this is a situation where the Gibbs energy of reaction will be less than zero no matter what the temperature is, because we have a negative value and we keep on subtracting something from a negative value. So we're just going to keep on getting more and more negative. If T is zero, we have a negative value. And if T starts to increase, we will get more and more negative. So this reaction is going to become more and more product favoring at equilibrium the higher T goes. In other words, this is less than zero for all T. All right. So the sign of delta Rg is less than zero for all temperatures. All right, so you don't have to put there for all temperatures, but it is less than zero for all temperatures. And that actually makes sense because combustion reactions are so spontaneous, so they occur spontaneous, they will lead to highly product favoring equilibria because they occur at high temperatures. So in other words, they will occur so rapidly, they usually form such product favoring equilibria that there's almost no reactant left. And that makes a lot of sense. All right. So let's look at the last part of the question. The last part asks, will the value of Kp be very large, very small, or near 1? And then will the equilibrium constant Kp for the system be larger or smaller at temperatures greater than 298 K? Explain how you made this prediction? Well, of course, because the Gibbs energy is so negative, right, or negative, no matter what the temperature is, that means Kp has to be much larger than 1, right, because our Gibbs energy of reaction is negative, right? It's product favoring equilibria. Product favoring equilibria means large K's. And the second part that says, if will Kp be of the system be larger or smaller at temperatures greater than 298? We just need to look again at this, how G behaves with temperature. So just writing that down again, if we look at G, it's minus T plus. So as T increases, our delta RG naught becomes more negative. Right? And if it becomes more negative, what does delta RG naught becoming more negative mean? It means that your equilibrium becomes more product favoring. Alright, so the fact that it's negative makes it product favoring. And then the size by how much it is negative is an indication of how product favoring it is, right? Just as the size of Kp is indication of how product favoring your equilibrium is. If Kp is like 17, you don't really have a very product favoring equilibrium. If Kp is like 10 to the power 34, you have a massive product favoring equilibrium, right? So if delta Rg naught is very negative, you have a more product favoring equilibrium, which means that your Kp becomes larger. Right, and you can actually see that in how Kp is calculated. If we recall that Kp is equal to e to the power delta R G naught divided by RT. If delta Rg naught is a negative value, then Kp actually becomes e to the power a positive quantity, right, divided by RT. And making it more and more positive means that you have e to the power a positive value. And e is 2.7, right? And 2.7 to the power a positive value is just going to become larger and larger and larger and larger and larger. And that's why Kp becomes bigger and bigger and bigger the more negative delta Rg naught becomes. All right, good. So that's all how these things really nicely link, and how you hopefully see how they interconnect, and how you should also understand them and have a good connection of all of these parameters. Alright, thank you for watching, and I'll see you in the next video.